It's a pleasure to be here. I'm an enormous fan of PyData. I used it so much over the years, and so the opportunity to speak is just fantastic. Um, as we mentioned, I'll be talking about revolutionizing the big data age with compute over data. Something that I think is really an unspoken or underinvested in work in our space. And I think it's really transformative to the problems that we're all facing today. So when I think about what the layout of the world looks like, it's really a lot like this. You see the amount of data and activity that's happening, literally every second. It's enormous. And with all of that happening, you're generating an enormous amount of data. And that data is getting even more substantial. You can see here that, based on some recent analysis from IDC, the amount of storage is reaching into the zettabytes, which is, I don't know, about 3 orders of magnitude larger than most people have on their personal machine. Just absolutely incredible amount of storage will be out there. And unfortunately, a lot of people approach the problem like this and say, well, I don't have a big data problem. I have a bunch of machines. They sit in a rack. They're, collecting a whole bunch of stuff. And so that may be true for now. But the reality is a lot of people don't think about how easy it is to generate, for example, 100 terabytes. So I did some back of the envelope math for this presentation. And to generate 100 terabytes in about 100 days, that could be any one of the following. It could be 1,000 nodes, each of which are generating 1 gigabyte of logs a day, which is not very much. Could be just 100 VMs, each of which have 10 services on them. Could be MySQL or your web server or a proxy or something like that, generating just 100 megabytes a day. 20,000 users uploading 5 videos. Each video is 5 minutes long. That'll get you to 100 terabytes. A fleet of 10,000 vehicles. The average vehicle today has 70 sensors on them. And if each one of those generate just 150 megabytes a day, or let's say you're in a real edge scenario with temperature sensors, cameras, so on, and you have 1 million IoT devices in your entire fleet, then you just need to generate a megabyte of data a day, and you're already at 100 terabytes. So generating it is quite realistic for a lot of people. And the reason I mention 100 terabytes is it takes an entire day using the average cross-sectional bandwidth of an AWS machine, 10 gigabit, to move 100 terabytes, an entire day. And once you get to generating this instead of in 100 days, but generating it in 1 day, if you're moving that data and the bandwidth hasn't dramatically improved, you're going to be facing immediate backlogs. And obviously that is not ideal. And I haven't even gotten to the cost. If you build your own on-prem data center with storage, it will cost you about $1.3 million to store that data store that petabyte over 5 years, which is really pretty significant. You're talking about real money at this point. And again, 100 petabyte or 1 petabyte is only 10 of those 100 terabyte per day or 100 terabyte chunks. So again, very realistic to get to and very, very costly. And that's if you have an on-prem data center. Now, what I would argue then is that both the time it takes to move it around as well as the cost to move it to some centralized location instead of keeping it on those remote machines isn't just recommended, it's the law. So your options today are use one of these many distributed clusters to achieve this and spread your compute to where the data is. And there's nothing wrong with these things. And there are many others as well. But the reality is that most data scientists, most engineers, and most software engineers don't really want to use them. They're perfectly fine for high scale, high throughput things, but they're definitely not designed for really developing and building your applications on top of. Just to use a trivial example, one of my favorite PyData, PyData toolkits is pandas. And you can see here to do the standard housing example in pandas, it takes literally 2 lines of code to get a mean. If you want to do the same thing on Hadoop, it's this. And it's not just this, it's actually even more than this. This is as much as I could fit into the thing. One is obviously far more approachable to achieve what you want. Now, I'm not dismissing what you're doing on the right. It's obviously a much, much higher scale problem. The thing on the left will not scale trivially to be embarrassingly parallel. But suffice it to say, as it stands right now, this is what we're presenting people. Either do the thing on the left and have very big hard drive on your local machine, or do the thing on the right. So then you might say, okay, but does this need to be decentralized? Well, in writing this up, I kind of approached it like this. If you look at the dictionary definition of decentralized, it's organizations whose activities are not performed in one central place, but may happen in many different places. And my argument is that these are already, many machines, many devices, many users, and all of them are decentralized. None of these exist by and large in a single data center. The data is already decentralized, and it's up to us to figure out what we're going to do about that. Now, you might ask, well, what is an example of what might happen here? So on the left, we have our data scientist, and she wants to run a single large processing job. You had over the top of these many clusters. In this case, I've just whipped together 3 clusters, each of which are writing to their local machines. So she says she wants to do her one data processing job. She hands it to her centralized cluster. At that point, the cluster needs to download from each one of those single machines, assuming we haven't pushed all that to a central repository. After that takes its time to download, even though it's being parallelized, it's still oftentimes going to peg your ingress bandwidth. But finally, she can start, and she does, and then she gets a result back, but oh no, she got one thing wrong, and she has to start over. And that might mean re-downloading all of those things again, especially if there was any time between when she rolled out that job and when she actually executed on it. Because a lot of times that intermediate cache or that intermediate download would be deleted because the amount of cost and the amount of space in that central cluster could be very constricted. So then you might say, well, okay, there's this thing called the cloud. Shouldn't I just use them and they'll take care of everything? They have unlimited scale and so on. And the answer is sort of. It's not like they aren't useful. As someone who worked at the clouds, I can say we have a lot of really good use cases for them. But make no mistake, it is quite costly to store that 1 petabyte of data on the cloud with no discounts or special backroom deals. It's going to be even more expensive than storing on-prem. Even assuming that you cut the amount of admin by half. The storage price for anything that isn't just glacier level of storage is quite costly, and we haven't even gotten to the processing. If you want to process that and move that into a higher tier of storage, you're now going to be paying roughly 4 times as much. So again, this isn't to say there aren't very specific and very useful cases that these cloud vendors can fill in. But making that the default for how we do these very big data problems is pretty substantial. And we need to have a solution that has a multi-tier approach to this problem. So yes, like I said, we need a system that maps to how we collect and store data today. So how tech can adapt to the big data era? Well, first, like I said, you're going to have all of these decentralized and distributed devices out there. And each one of those are going to have their own amount of storage. Now, again, they may not want to store, hundreds or, thousands of runs or files or things like that, but they can certainly store what they're already downloading before they do a final upload. And so being able to execute in that location is pretty profound, and we should figure out a way to do that. Second is around incentive models. So this isn't just about, can you do things in a centralized way or decentralized way, but really think about it even more broadly than that. Could there be a way for the ultimate clients to, basically contribute their own compute or their own storage or whatever to those to your eventual path? And there are lots of ways. It doesn't just have to be some kind of payment. You could say like you're joining an overall group of people, you're donating your stuff to charity. There are lots of things like that, and we need to figure out a way that doesn't involve everyone filling out whatever a 1099 in order to contribute their powerful Macs or PCs to the problem. And then third, we need a solution that is provably secure and verifiable. What do I mean by that? Well, in this decentralized world, you have a realistic problem where things might be untrusted. And by untrusted, I don't mean that someone has necessarily hacked into your data center and has a virus on a machine. So that certainly happens. But making sure that, number one, the people who need access to the data can run against it, can do so without, for example, exporting everything to a CSV and dropping it in an S3 bucket. But second, also that the data that is running and the jobs that are running on those machines are doing it in a reliable and secure way. That maybe you want to open this up to allow your partners to run code. You want to be able to do that securely, isolate exactly what's going on. You want to make sure you're not leaking data out the side door, and so on. There are lots of security problems there. There's also the verifiability problem, which is, if you think about it, this is something that a lot of people who maintain a small number of machines may not have seen. The ability for a fleet of machines to get out of sync quickly happens all the time. They could be disconnected from the network. They could have the wrong version of a driver because something didn't install properly. They could, have a particular architecture that, your latest build doesn't support. And what happens there is not that the thing, the best case scenario is you attempt to run and it gives you a very clear error. That really is the best case. The nightmare scenario is that you deploy your job to this thing and it runs, but it runs it in a bad way. It's got the wrong driver. It's got the wrong this. It's got the wrong that. It can't read. Yet it doesn't respond with a clean error. It responds with an empty file, or even worse, it responds with something that's just wrong. And in the case where you're doing it on 50, 100, 1,000 machines, that's simply something you cannot look at and discover that is right or wrong. Because if you knew the answer, you wouldn't have run the job distributed in the first place. You need a way to verify that the code you ran correctly and can report back. So all of that together is what we're talking about when we talk about compute over data solutions. So how does this look? Well, first, we need a pipeline to declare a job and a pipeline in a portable format. So if I'm running on an M1 Mac and I want to deploy this to a set of ARM or a x86 or some specific system on a chip that my hardware vendor has provided, I need to have this thing be portable, be able to run against all those variety of types. And so what we need is something that absolutely reproduces the job and the pipeline that I have detailed and has a spec that can be portable to any final location. Second, I need to be able to start that job in any place, including one which may have a bad network connection or unreliable or a heterogeneous networking, heterogeneous compute, those various problems, and ensure that it completes. And if it fails halfway through, verify it and boot it out, or maybe rerun it or whatever it is automatically. And third, once it finishes, I need to be able to trust the results. And that means we need a network that is incentivized in some way to complete the job. It can't just be volunteer. It's got to be something that people chip in. But also the network needs to be verifiable. So even if there is an untrusted thing or something that's out of scope or out of version, I'm able to verify it automatically, that the system doesn't require me, manually walking over these things. We need a system that builds all three together. And it can't require rewriting everything. As we saw in the other distributed systems, If it does require rewriting everything, I think you're going to have a lot of really unhappy engineers and data scientists and so on who are trying to do this, because instead of doing their job, they're going to be off rewriting stuff, into whatever version of Java, the thing requires. So how does this look when you build against a compute over data network? Well, it looks, here's the layout that we saw before with our data scientist or our developer overseeing 3 networks. And she has access to this compute over data network. So she says the same thing. She'd like to start her one data processing job. She hands that to the network. And I'll leave what the network is as an exercise to the reader. I'll talk about it in a little bit. One example of many. But that network then takes the job and says, okay, here it is. I have a new job. This job has a content addressed ID, a unique hash that describes the nature of the job. And it has 3 chunks, and it offers it up to the entire network. Now, node number 1 in data center 1 says, oh, I have chunk number 1. I'll take that. Node number 2 says, I have chunk number 2. I'll take that as well. So off we go. Now, chunk 3 is on this node over here, but this node doesn't have any CPU space. And this one doesn't have the 3rd chunk of data, but it does have CPU to spare. So we need these 2 nodes to automatically recognize that in each other and pass the data between the place where it is and the final location. Instead of migrating all 3 nodes back to some central location, it's just migrating this 3rd one. It finally migrates it over. Now this node has both the CPU space and the disk necessary, and it can execute. We run the processing job in an embarrassingly parallel way, so all 3 machines are executing simultaneously. And all 3 are now done, and says, here's the content addressed ID of the results. And then we have someone else in the network step forward and say, okay, now that you've done that, I'm going to verify the job and execute a proof to ensure that this was actually run and the data is correct, and whatever criteria the original data scientist or developer set up in order to run that job is able to take it and come back. And so they verify the job, verification done, passes that back to our data scientist, and she says, awesome, and is ready to go. Each node now downloads the results, not the original 100 terabytes, but whatever derivative might be involved to that thing, and she's able to move on with her work. And again, this could just be the first step in a multi-tier architecture where instead of handing it back to our developer, she instead puts it on a much more high-performance cluster to do additional distributed things, Hadoop or Spark or whatever, using maybe she wants to do training on it or things like that. So again, it's not an either or. There's no question this step has to exist. Today, it basically only exists on one of those platforms you saw earlier. But I believe that we need to build a more decentralized network that is able to accommodate these things. When we do this with these auto healing, auto repair, and auto organizing system, I think you get a lot of benefit across many vectors. First, it's much easier to manage. The network self-organizes. It's already compatible with existing tools and has built-in verification, which is critical. You don't have an administrator being a gate to amount of time and so on that she has available. Second, it's far more cost-effective. It's kind of serverless-ish. It's much more efficient at finding the space in the network that has available CPU or disk. And as you saw, much reduced ingress egress, obviously one of the highest costs for a lot of folks. But then finally, it's much more reproducible. You can, everything here is content addressed, everything here is collaborative. You can do a whole bunch of very powerful things with reproduction because you know exactly what it was you ran your job on, your data and so on, and you're able to come back and run it again or not run it again because you know that nothing has changed. Additionally, you can build in a lot of metadata and lineage tools, which are super powerful. Something that we lack a lot of, particularly in the export to CSV problem. There's almost never lineage around that. But you can also get a lot of communal funding models. I touched on this is, you could argue that this is exactly what SETI at Home or Folding at Home did originally. They had a centralized amount of data. They passed that to end users. Those end users were able to run small processing jobs on them and contribute back. And they did that in a communal way. And that's certainly something that we can do as well. So we have right now what we call a compute over data working group. There's a link at the end that will show you how to do it. Here you can see we already have 16 people, excuse me. 15 here, but you'll see we actually added some since I put the slide together on the compute over data working group slide site. We meet every other week to talk about these things. And we're really excited about joining together. This really isn't an either or thing or really non-competitive. We want to join with everyone to build solutions for this problem. So you might say, okay, well, you showed me a bunch of people. What's the one true compute over data? And the truth is there really isn't one. In addition to all those folks that I showed earlier and the ones that you just saw on the compute over data thing, what you have is the reality of something like this, where there's a real a spread across these various compute networks, where you really have an approach where you make a choice between privacy and verifiability and performance. And each job that you approach may choose a different one of these. And each network, we expect, will fill in somewhere in this overall bucket, where maybe you choose higher privacy or higher verifiability or performance, but you're going to have to choose one. Sitting right in the center, you can, but then you don't get the optimization across any one of those. And that's really up to the person to decide exactly what the nature of their job is and how much they want to pay and how long they want to take to do it. And really the options just start there. You really have other things as well. Like we said, you can have different incentive models, social good, charity, and so on. You have different segmentation models. Do you want to go really broad to make this something that anyone could use? Maybe you do it very depth, where it's very large enterprises who want to run this all on-prem. Maybe it's a regulated industry. Or finally, you have different requirements. Maybe things need to all stay within the boundaries of, I don't know, Switzerland, or need to stay within HIPAA organizations or something like that. Different hardware types, or maybe you want to select and say, I only want to run this on green compute over data networks. So with that, I'm proud to announce that we do have one in market today. This is the one that I'm running. And again, this is just one of many out there. But I do want to talk about what we have. And, in my opinion, it's certainly a contribution to the overall network. We actually just hit beta. It's called Bacalhau, which means cod in Portuguese, cod, C-O-D, compute over data. That's the joke. And the idea behind Bacalhau is to help provide one of these things. You can do any of a whole number of things already on Bacalhau. So in this case, what you see here is me executing a Python job on the Bacalhau distributed network. And you can see here it's very, very straightforward. I just type this word, Bacalhau. I have to do a quick installation, which is pretty straightforward. And then I can run this arbitrary Docker container from the Docker repo, this Python executor, and say I'm run a Python job, and it's able to do it. I can also import a whole series of files and do that as well. Or I can just hand it a script and run that as well. And so again, the idea here is that it's very, very portable. I didn't have to learn anything else other than potentially, adding a few words to the beginning of my, Python script, or excuse me, with my CLI that I would normally do. Nothing else changes. You can see here, everything else is just running exactly as is. I can do R on it. Here I am using an R script that I can upload, and off it goes. Here I am doing pandas, for example. In this case, I have two files in my pandas directory, a Python file and a CSV. I'm going to upload those to IPFS. That's the free globally distributed IPFS network, which has more than 18 exabytes of space on it. So I'll upload that there, and then I can just run that job. And in that, I'm going to use pandas to read that CSV in and print out, a series of transactions. And I do that there. So again, no translation. I didn't have to, rewrite my script. I didn't have to do anything. I'm just magically using a decentralized network. Maybe I want to use DuckDB. This is a crazy cool example where DuckDB is an enormous amount of flexibility and usage. A whole bunch of different people are using it out there to use arbitrary SQL queries against a Parquet file, or excuse me, any flat columnar file. And you can see here, I'm just doing select count from yellow taxi Parquet, and there I am. You see, I've run that job on a, maybe it's a much larger machine than I have access to. Just, an 8 GPU machine with 8 gigabytes of RAM. Here I'm going to do inference against YOLO, and here you can see I'm just running it against an arbitrary image here. I could run it against whatever 10,000 images, all on these remote machines, and it's ready to go. I can also do it build AlphaFold. So here you go, right? Using Docker run, I do it against a single GPU machine. Here's all the weights and the databases, and I hand it off and run it. And presto, I'm now running AlphaFold. Again, I didn't have to download anything. This is a 2.5 terabyte AlphaFold database that I didn't have to spend my time downloading. I just ran it on the system that was already hosted out there, and off it went. And you might ask, is this a cryptocurrency thing? And I promise you, no, it is not. While cryptocurrency and overall cryptography is key to our system, all these machines and things today are things that we already support, and today require no interaction with cryptocurrency in any way. Now, that said, we know the Web3 community is very interested in this, and we will certainly give them a great home here to do a whole bunch of different installations and jobs against it. But the truth is, we want to transform data processing by giving developers simple, low-cost, distributed first tools that unlock a collaborative ecosystem. We will help cryptocurrency and Web3 people achieve that, but we will also help Web 1 and Web 2 people as well, because it is critical that if we're going to make progress against this very fundamental problem, we have to support all comers. And I can't stress enough that we are more than open to working with anyone. And with that, I will wrap up. I actually don't know if I can take questions, but here you can see a whole bunch of stuff. You can also see some QR codes in the upper right corner. You're more than welcome to scan those and jump over. They'll link to things that are on the slide and so on. But we'd love to hear from you and love to see if we can support you in the near future.